Welcome everyone to week 2 of financial management. I'm on schedule, so today's schedule calls for me to cover Chapter 8 risk and rates of return and capital market theory, so that's what I'm going to do. Before we do that, I was going through my folders getting ready for today's class, and it's one of these things, you're looking for one thing and you find another thing. Well, I found something last week. I talked about, one of the things I talked about is what's the goal of a firm, and in there I said ultimately the goal of the firm is to what? Create value for the shareholders, measured by the long run price per share of the common stock. You're gonna tell me that on the exam, I hope, when I ask that question. But as a previous goal, I said sometimes some companies, the goal of the firm is for management to take care of managers and to pay themselves some pretty good money. Well, this is some data that I must have found last year and I forgot, and you can take a look at it and bring it in a little bit tighter. I'll move it around so we can highlight the people. I'll blow that up. Here we go. We get it right. This was the #1 paid guy in the United States last year. Philippe Dauman. I guess my French is no good, but he made $84.5 million last year. And his company was Viacom, which is, I don't know, whatever Viacom industry, type of thing. And then Ray Irani, I believe is the way he pronounces his name, from Occidental Petroleum, which is an oil company, but it's certainly not the biggest oil company. It's a good-sized oil company, but not the biggest one. And his was $76 million. Now, let's see, $76 million. That's about, what, $1.5 million a week? 2 weeks, and I'd be ready to retire. I think. And Lawrence Ellison from Oracle, and your generation knows Oracle, $70 million. DirecTV, which is not, that's how we get our satellite communications, 33 million. Black & Decker, which makes power tools. I needed a new drill for my place down in Florida, and I bought a Black & Decker drill just before I came home, and it was cheap, which is what I am also, and he, $33 million, and a couple other ones I've got on here. Brian Roberts from Comcast, and the amount of money he makes from my charges ought to be enough to pay most of that salary that he pays. Feels like I'm paying that much myself. And then Walt Disney. Walt Disney's an interesting company. Of course, we've all heard of Mickey Mouse, and we've all heard of Disneyland and Disney World. But that company also owns some other companies, one of which is ABC TV. So if you watch television, ABC Network is owned by Disney. And then ABC Network owns ESPN, the sports network. So, and then there's ESPN2, and they have about 4 or 5 different ESPN channels out there. So there's a lot more involved there than just Mickey Mouse type of thing. Call it a Mickey Mouse company, but he only made $28 million anyway. So there's a lot of money to be made. And I think this was data that I got last year, and I probably get some data in the next week or two out of the Wall Street Journal for this year, but that was just some stuff I happened to see there. So there's some evidence. I think that's some pretty strong evidence that some companies, at least the top managers, have their eye pretty good on what they're getting paid. So there's a lot of evidence. But in this class, the goal of the firm is create value. Do something for the stockholders, and we're going to measure it by the stock price. So that's basically what's going on. All right, today what I want to talk about is risk versus rates of return. And I'm going to give you 3 versions of it. I'll just give you the highlighting of the 3 versions of what I'm going to do. The first one I'm going to give you is what I call the classical version. And that started approximately 1600 up until about 1950. So for about 350 years, this is pretty much the way people talked about risk and rates of return. And what I'll try and do is not just give you the theories, but I'll try to give you a little historical perspective. Who were the people involved and what were they thinking about when they thought about it? If I could really earn my living for what I enjoy doing, I would teach history. Except history teachers don't make any money. So, and being a finance person, I am interested in making money. So I don't teach history, but that's what I really enjoyed doing. The second model is called portfolio theory. And that was the 1950s. And to your generation, 1600 versus 1950s, it's all ancient history. you can't relate to it at all. I was alive in the 1950s, and so this doesn't seem quite so ancient a history to me, but to you it does seem a lot like the ancient history. And then the third version of what I'm going to do is called the capital asset pricing model. And this started in the 1960s, and there are some new things coming out on it right now. They're still working on it. Things didn't stop 50 years ago, but it's still pretty much on the edge of what's going on. And when we get down, I'll try and point out to you that some of the things that they're thinking about now, which will end up eventually being a different kind of a model, but it's still the model that's pretty much in vogue. So these are the things that we're going to look at. This classical version, I won't talk much about it. Portfolio, what's a portfolio? What does the word portfolio mean in English? Well, it's a group of investments. So the word portfolio, and when we use the word portfolio in finance, we mean some kind of a grouping of investments. So classical version, then we start thinking of investing in terms of groups of investments. And then capital asset pricing model. Well, an asset, you should have some idea what that is. That's something that adds you some value. The word capital asset means stocks or bonds. Stocks, bonds, and other things, other ways we can make money type of thing. So it's those financial ways that we make money. So the financial assets and the pricing models means this is the way we figure out what they're worth. So capital asset pricing model, it means it's kind of one of the bases for trying to figure out what a share of stock or a bond or whatever that might be, some idea of what it's all about. So this is kind of what I'm going to be doing here today. And hopefully you remembered to bring the homework pack that I gave you last week, because if you flip a few pages in there, it says risk and rates of return problems. And in class, we will take a look at problems 1 and 2. 1 and 2 are my class examples, and then the rest of that set, 3 through, I think it's 7 or 8, I don't remember which it is. 7, 3 through 7, those will be quote-unquote homework problems. And homework problems doesn't mean that you do them and then send them in to me and I grade them. It just means here are some ways that you can practice on these problems to prepare you for the exams, and there's some little numbers on each problem which give you an idea what the bottom answer should look like, so that you know what if you got the right or wrong answer when you finally got down there. So that's kind of an overview of what we're going to do here today. So let's kind of get started into this concept of risk versus rates of return. Go ahead, I'm going to just talk for a bit here. Last week I gave you seven principles of finance. Is that what I gave you? 7 principles of finance. And number 1 was the risk-return trade-off. And I said you better figure out, have some idea what's meant by that, and an example of that. Well, a lot of what we're talking about here, especially the classical model, is the development of that principle number 1. So the classical model and the risk-return trade-off are basically the same thing. So it's basically principle number 1. And then I had a 7th principle which said all risk is not equal. And I said, I'll explain that next week. Well, this is next week. And that's really that third model, that capital asset pricing model, is the explanation for the capital asset pricing model is going to be the explanation for principle number 7. So when I get to that third model and I start explaining it and show you where it came from, I will, when I get all done, I say, okay, I just explained principle number 7 to you. So you can cross-reference from one week back to the other. I'm just trying to give you a little bit of a heads up. So those are the two principles we're going to focus in on, principles 1 and 7 here tonight. Now, the classical theory. The classical theory started back in about somewhere around 1600s, which in the Western Europe was kind of Renaissance time. It's when we all the people started thinking about different disciplines. For those of you that are engineers or math majors or whatever that might be, or use mathematics, and you've had to take courses in calculus, it's about the same time that calculus was being developed. And the point I'm trying to make is there were a lot of really, really bright mathematicians in Western Europe at that time. So in Western Europe, a lot of really bright mathematicians. Now, I don't want to say too many negative things about different disciplines, but if you're a really bright mathematician, you're really smart, but you probably don't make a lot of money. So we had these people that were developing modern mathematics that were really, really smart, really, really bright, that didn't have a lot of money. And they said, maybe we can use this mathematics that we're developing here right now, and maybe we can use this to make some money. Well, one of the best places to make money back in the 1600s and back in that era was to go to a casino, like Monte Carlo, and there's another one in Baden-Baden, right on the border between France and Germany. And if you really knew your mathematics, these guys figured, well, we can use this mathematics that this thought process we got, and we're going to beat the casinos. Now, they didn't do really well, but just as an aside, back there, about 30, 40 years ago, some really smart people at MIT figured out how to beat the casinos. There was a movie on that. Anyone? Right? Any of you people? 21. What was it called? 21. Blackjack. Well, the Blackjack is 21, but there was a movie about these guys actually beating the casinos.
21 was the name of the movie.
21 was the name of the movie? Okay, I don't remember. I remember reading about it, and then I saw that there was a movie about it, type of thing. So they were only like 400 years late doing it, type of thing. It took them 400 years to finally figure out how to beat the casinos. But these guys were going to try and beat the casinos back there in the early 1600s. And through all their efforts of trying to beat the casinos, actually that was kind of probability theory is where that whole thing eventually came from, and then statistics and all that. So from people trying to make money at Baden-Baden and Monte Carlo and the other casinos in Western Europe, this was the development of probability and statistics. And I probably didn't have to tell you that probability and statistics never came from any good anyways, so that you probably never liked it anyways, and now this just confirms your thought process that it was only good for beating the casinos. It was never type of thing. Okay, so we had these people doing it, and they start asking themselves some questions. And the first question, so this is what you have to get in your notes here. The first question they asked is, what is risk? What is meant by risk? So everybody start thinking, we got big, people are using that word, it's too risky an investment and all that kind of stuff. And so the mathematicians they ask the question, what do we mean by risk? Sometimes people say, I won't make that investment. It's too risky. And these mathematicians thought about it and thought about it and thought about it. And their answer was, anytime we have variability in our returns, anytime we have variability in our returns, we have risk. Now, let me talk about that. Just come straight ahead here for a little bit, because people get a little bit confused. If I ask you, you want to make a bet on this happening or that happening or double or nothing on your salary or whatever it might be, the answer is, no, I don't want to do it. There's too much risk. And when you think of the word risk in your mind, you think of bad things happening to you. bad things. I'm going to lose. So when somebody says that this is too risky, you immediately what you're thinking is something bad's happening to me. But when I define risk, I set variability in returns. Variability. Not only bad things happening is risk, but better than expected is also risk. So if I expect to get paid $50,000 next year, and I only get paid $30,000, that's a bad thing to happen to me. That's variability in my salary, and that's risk. If I expect to get paid $50,000 and I make $90,000, well, that's putting a big smile on my face. But also in finance, and way back there in 1600s, that was also risk. That was also risk. So risk was any time we had some kind of waving or a variability in our returns. Always. Okay, so keep that in mind. Anytime there's variability. Now, when we talk about what they're really working on now, the very last thing is they're kind of truncating that and eliminating the good things. So the way they're trying to work with risk now, I guess if we talked about a fourth model, is they're truncating it, and they're really only worried about the bad things. Is anytime you do better than expected, you all say, hey man, give me all the risk like that. You can say, if I expect to make 50,000 and I might make 70 or 90 or 110 or 200,000, I love that kind of stuff. But in the current world, we're truncating all that off, and we're going to do that. But for now, anytime there's variability, anything it's different than just that one expected thing, that is risk. Okay, so that was the very first. What do we mean by risk? It's that variability in the returns. The second thing is, how do we measure risk? Now, these are real questions back 400 years ago. People hadn't really worked their way through these things, and we were just coming out of some really tough times in Western Europe, and now we're getting to the point where people have some leisure time and can think their way through things, and this is the era is going on. And I said, well, really these were not only mathematicians, but they were people working on probability and statistics. So what they came up with is the way we measure risk is, the answer for that was the standard deviation of returns. If you had a course in probability and statistics, you've probably heard of the words standard deviation. Might have given you heartburn somewhere along the line, but you've probably heard of that phrase someplace along the line. So what they came up with was standard deviation, and my very first job teaching many, many years ago was I taught probability and statistics. And I taught it in the East Coast, in a city on the East Coast, and it had to be a city that had a lot of Greeks in that particular locale. And the class that I taught, one night class that I taught, was almost entirely made up of Greek students. And what kind of symbols do you use when you're doing probability and statistics? It's all Greek letters, alphas and betas and whatever. So bear with me, because I was teaching this stuff, and finally a hand went up and they said, we hear the words you're saying and we see what you're writing on the board, but the words you're saying and what you're writing on the board aren't the same. Meaning my ability to make Greek letters is non-existent. So I'll tell you what I call it, and this is the way I make it. You can make it any way you want, but my Greek letter. Okay. Standard, what's the Greek symbol that the statisticians use? Lowercase sigma. Now, I've never been able to make a lowercase sigma, but I can make the number 6. So what I do is I take the number 6 and I kind of rotate it on its side a little bit. So my sigma looks like that. So I'm going to use that for my Greek letters, sigma. So when I was doing that for the Greek students, they kind of, it's not a sigma, but bear with me. I'm going to call that a sigma, okay? So what they said is, risk is variability. We'll measure that risk with the Greek letter sigma. Okay, everybody kind of good with that. And for example, we could draw a probability distribution. Is that a word you ever heard of before? Now, you can do this for any shape probability distribution you want. It can be horizontal, it can be squiggly, it can be all kinds of things. I'm just, for argument's sake, going to make one that looks something like a normal distribution. I don't make them very well either, but this is my attempt. That isn't bad. I don't normally make them that well. So that's my. But it can be any shape to the distribution. It doesn't have to be this one. Now they came up with some Greek letters to kind of describe that probability distribution. One of the letters that they came up with was what measures the middle of that. And well, they called it the mean, and they once again used the Greek letter, and the Greek letter they used was a mu, and to me that's a lowercase u with a tail that drops off. That's the way I make it. So I'll make a lowercase u, and then I'll drop the tail on it like that a little bit. So that would be the middle of it. That's the Greek letter mu. And then they said the standard deviation is going to tell me how spread out this distribution is. And so that kind of measures this kind of thing. So the mean measures where the middle of it is, or the average, or the expected value is. And how spread it out is that sigma, and that's we're going to call our standard deviation, using a little bit of shorthand on it. For example, supposing I had two distributions. I told you I don't make these very well. Let's assume what we'll call one as mu A, and we'll say they both have the same middle. So these two distributions both have the same middle. More or less on my graph like that. And this will be the A one, so this will be sigma A and sigma B. Now what's the relationship between sigma A and sigma B? Well, sigma A is less than sigma B, is that right? So we could say then that the risk of A is less than the risk of B, something like that. So going back into the 1600s when people start going to the casinos, they said, well, anytime I had more risk, B's got more risk, I better get more return if I'm going to do that. So it's a risk-return trade-off type of thing. Come ahead and let me just give you an example of a casino. It sounds like I go to the casino every night of the week or something like that. And I've actually watched the roulette wheel a few times, and I don't even know how many little things there are on a roulette wheel. So maybe someone here in class has been to a casino can inform me about that. But two ways you could gamble is you could have a coin, let's say a quarter with a head or a tail. And another way you could gamble would be a die, not a dice. A singular dice is a die, D-I-E. And that just means one of those 8-sided cubes. Now, which has more risk? The tossing of the coin and catching it and calling heads or tail, or the rolling of the die, where I have, how many possible outcomes do I have on a die? 6. So I have 6 possible outcomes on it. So I have, which one has more variability? Well, the tossing a coin is only 2, it's yes or no, A or B, or however you want to say it. Rolling of the die, I can get 1, 2, 3, 4, 5, or 6. So it's got more variability. So if you're going to be in a game where they're rolling dice, the more dice they have in there, the more possible outcomes, more the variability is. And you've got to get the one correct answer. If you get that one correct answer, since there's enormous variability, the theory that they had back in 1600 said, well, there's a lot more risk with 2 or 3 dice than just a tossing of a coin. If you're going to call that rolling of 2 or 3 dice to get that number correct, you better get compensated for that greater variability. And so that was back in the 1600s. And that was kind of the beginning of the concept of a risk-return trade-off. So that was where people started doing those things back about 400 years ago. But we're still not done. In approximately, it was like 1724 or something like that. I don't remember the exact date, but somewhere 1720 something. And even though I like history, I can't remember every date perfectly. There was a guy that wrote an article, and at that time, they didn't write it in English or German or anything like that. The educated people in Western Europe all wrote in Latin. So if you want to read the works that people did back in the 16 and 1700s, you actually have to study Latin. Well, I did study Latin, and I can't read any of it anyways. Doesn't matter. I studied Latin for 4 years, and what I remember of it, you could write on a postage stamp. I don't remember much of it, but there was this guy, he wrote it all in Latin. Fortunately for people like myself, it was translated into English, so I can now read this guy's work. And the guy's name was, it's a name that some of you are going to be familiar with from some other coursework. His name was Daniel. Anybody in class that would like can jump in with his last name here. B-E-R-N, anyone have any guesses here yet? O-U-L-L-I. Daniel Bernoulli. Some of you might have had it. We have an electrical engineering professor. Did you ever hear of Daniel Bernoulli in electrical engineering? Never heard of Daniel Bernoulli? Yeah, you heard it, right? Yeah. He made life miserable for electrical engineers. He made life miserable for people in fluids area, and he also made life miserable for probability and statisticians. And in many respects, we don't usually brag about this, but in many respects, he was really the first true finance person. So he was, in many respects, the father of finance. That's a very little known, because all the electrical engineers and the statisticians all brag about Bernoulli, but finance people, he's also kind of started. So he's very, very much a Renaissance person, did a lot of very interesting things. And he got looking at, so Daniel Bernoulli, you can come straight ahead for a little bit while I start talking about it. But Daniel Bernoulli started thinking about the work that had been done in the previous century. And he said, well, you know, if we got more risk, we got to get more return. But he said it's even a little bit more complicated than that. He says, okay, let's supposing you've got something that's a given. So your salary next year is a given, $50,000, say. And then someone comes along with a coin and says, double or nothing on next year's salary. So you can either have $0 or $100,000. Now, if it's a fair coin, 50-50 chance, the expected value, 1/2 of 100,000, 1/2 of 0, is still $50,000. So that what we would call a fair game. So for someone to walk into you and say, I got a coin, we'll flip it in the air. If you call it correctly, I'll double your salary. If you call it incorrectly, you get 0. In either case, you do the same amount of work. And that's a fair game. Your expected value, your average income, would be $50,000 in either case. But he said you'd be a fool to do that. You'd be very unwise thing to do that. Now, you people are going to say, well, there's too much risk. And in a sense, that's what Bernoulli came up with. But why is there too much risk, and why does it not make much sense? All right. Let's say you've got that salary guaranteed at $50,000 a year. And somebody comes in and says double or nothing on that salary. Well, if you're making $50,000 a year, you have a standard of living. You have a place to live, you have clothes, you have food, you have entertainment, whatever $50,000 will do, you're guaranteed that you can have that. What if you call it correctly and you go to $100,000? What happens to your standard of living? You're better off. It goes, if this is what it is at 50, 100,000, we're better off. So my standard of living goes up. But what if I take that gamble and I lose, and my income now goes to zero. What happens to my standard of living? It goes down, right? I mean, if it really goes to zero, I'm really in deep trouble. So it goes from 50 to 100, it goes up. It goes from 50 to zero, it goes down. Now, this is where Bernoulli made his big contribution. Which number is bigger? From 50 to 100,000, the increase in the standard of living, or from 50 down to zero, the decrease in standard of living? The decrease. The decrease. So even though it's a fair game, and even though your average income is the same, if you did it 2 years, 1 year when you had 100,000 and the next year you had zero, well, if you spent 100,000, your standard of living went up that year, and you had zero, your standard of living crashed and burned. Your average between those two would be less. You would have a lower standard of living, than the person that just took $50,000 a year. And that was a really big change. And what Bernoulli said was, it would only make sense to take on risk. And this is principle number one. It came from Daniel Bernoulli. It only makes sense to take on that additional risk if you get even more return. For example, what if I told you the coin 4 times out of 5 turned up heads? And you can call it. So you're going to call heads 4 times out of 5. Well, what's your average income now? Well, 4 times 80% of the time you'd have 100,000, and 20% of the time you'd have zero. Your average income now is $80,000. And some of you might say that's a worthwhile thing to do. But that's that risk-return trade-off. That's what we mean by the risk-return trade-off. It does not make sense to take on risk. And that's principle number one. And this is Daniel Bernoulli back approximately 1724 in this article. And he's the one that said it. And it seems quite simple to us now, but in 1724 it was a very original, earth-shaking thing. And thus, in 1724, he says, the only time it makes sense to take on additional risk is if we get compensated more. Somebody's giving us even more money, so our expected income goes up. And that's that risk-return trade-off. So that's what we mean from it. So classical theory gets traced back to 1724, Daniel Bernoulli. That's the risk-return trade-off. So somehow figure out how to put all that in your notes. I'll give you a few seconds, or you can make yourself some notes so you can remember what I just said. I don't know how to do it concisely. But the risk-return trade-off says that. Bernoulli says because it's the standard of living, your level of satisfaction is important. And your level of satisfaction goes down more than it goes up on the good side. And thus, we got to really do really well on the upside to compensate for going down on the downside. That's that risk-return trade-off, and that was principle number one. So from about 1724 up until about 1950, which is what, about 225 years, this is the way people thought. A risk-return trade-off. Anytime I take on more risk, I got to really be compensated with additional return. Principle number one in finance. Now, let's suppose you were in the United States, you weren't in the United States, your great-grandparents were in the United States, or your grandparents were in the United States, working for a major company back in the 1930s, 1940s, somewhere in that era. For example, your parents or your grandparents worked for General Electric or General Motors or one of these really big companies, and they had a pretty good job. And they made enough money that they were able to save a little of that money. Now, what would they do if they were able to save some money back in the 1930s and 1940s? Well, if they were smart, which not everybody was, but if they were smart, they would invest it. So if you had a little money back in the 30s, which was the Great Depression, so there wasn't a lot of people with a lot of extra monies. 1940s, there was pretty good economic times in the United States, so some people had some pretty good chunks of money. But back in that era, if people had extra money, where did they invest it? Well, they looked at their risk-return trade-off. They'd look at all the different stocks and the different bonds that were out there, and they would make a decision where to invest it. Now, most people, and in fact, almost everyone that I know from back in that era, now it's a little before my time, but from talking to my aunts and uncles and grandparents and people from that era, people that lived in that era, the ones that had some extra money and invested it, most of them have invested in one company. And so they would look at the different companies available for them to invest in. They would pick one company, and they would say, for me, the risk-return trade-off looks best in this company. And what happened was that back in that era, the company that most people chose was the company that they worked for. So if you worked for General Motors, you bought General Motors stock. If you worked for GE, you bought some GE stock. If you worked for one of the oil companies, you bought oil company stock. And if you were lucky and that company did well, you not only had a good career there, but the value of your stock increased and you managed to accumulate a fair amount of wealth. And I knew a lot of people. I come from big families. My father's family had 10 in it. My mother's family had 9 in it. So I come from really big families, and I knew a lot of people from that era. And some of them, not all of them, but some of them were fairly lucky, and ended up making a fair amount of money from back in that era. And almost every one of them, if they had extra money, they bought stock in the company in which they worked for. And if they were lucky, that company did well, and so forth. Now, when you think about it, that was a really dumb thing to do. Now, why was that a really dumb thing to do? All right, I worked for General Motors. Let's say I worked for General Motors. This used to be General Motors Institute. So back in the 1940s, I worked for General Motors. GM was making a lot of money, and its stock was going up, and so forth, and my career was getting better. And so I made a lot of money on my job, and I made a lot of money on my investment, and I probably, if I were doing that back there 70 years ago, I probably had fairly successful when I was, by the time retired type of thing. I lived quite well. But what if I were unfortunate enough to work for a company that didn't do so well? Maybe I worked for another company, presidential candidate Mitt Romney. His father ran American Motors. Well, American Motors was around that era, except American Motors isn't around anymore because it went out of business. It wasn't as successful like General Motors. And so supposing your great-grandfather worked for American Motors and had a good job, saved some money, and bought some American Motors stock. What was the problem for your great-grandfather? Well, eventually his company went out of business, and he lost his job. And the money that he put into American Motors stock was now worth nothing. So you lost money on the stock, and you lost money on your job. You couldn't have made a worse investment. And people didn't realize that back then, but that's what everybody did. If you worked at a company, you had extra money, you bought stock in that company, and it turned out that that was a really dumb thing to do. And that leads us to our second model. And if you want a particular year for it, I wrote down 1952, but it's none of these things actually happen in an instant. They take years to develop type of thing. So over somewhere starting in the late 40s through the early 50s, all this work was done. And there was a guy whose name was Harry Markowitz. I won't make you spell his name on the exam, so don't worry, you don't have to know how to spell Harry Markowitz. He did a lot of writing in this whole area, and almost every article he wrote had the phrase portfolio theory in it. So in the early 1950s, Harry Markowitz looked at what people have been doing in the 30s and 40s, and he said, boy, you people are making a mistake. This is not the way to invest. And he came up with this concept known as portfolio theory. Now, the way I'm going to explain this is with a numerical example. And this is what Harry Markowitz did in his articles. Back when I was in grad school, I had to go back and read all these original articles and so forth. I'll spare you that grief. And I'll take the example that Harry Markowitz had, but I'll clean it up so that the numbers aren't as bad as what you would have had at that time. Okay. He used the lowercase r for the return. And he had two companies. He had Company A and he had Company B. And he said the return that these two companies make is 12%. This is the return. You could also call this mu A and mu B if you want to use the Greek symbols for it. So either way, here's the return that you would make. And then he said the risk of A and the risk of B are exactly equal at 30%. And he said, all right, you've got some money to invest. How are you going to invest it? Are you going to put it all into A? Are you going to put it all into B? Or are you going to put it some into A and some into B? Now, if you look at it, they both have the same return. They both have the same risk. So on the surface, it doesn't appear to make any difference. I mean, they both have the same average return. They both have the same risk. What difference does it make if I put it in A or I put it in B, because, and so forth? And he said, not so fast. He says, let me define one more value for you, and it's a capital letter X. And he says, it's the percent invested in A. And actually, I prefer to do it as an index number rather than a percent. So I have X going from 0 to 1 as an index number. So it's 0, 0.25, 0.5, 0.7, which is 0, 25, 75%. Either way you want to do it. You can do it either way, okay? Incidentally, what would be the percent invested in B? Some people want to call that Y, but you don't need to, because let's say I put 30% of it in A. How much do I put into B? 70%, right? Because I got and where do we get the 70? Well, it's 100% minus the 30%. So what we do, we go 1 minus X is the percent in B. Now, what we're interested in is we use the letter P for portfolio. And what we're interested in is the return on the portfolio. And sigma P, the risk of the portfolio. Now, if you remember statistics, this is not hard. If you don't remember statistics, the numbers get terrible for you. And it turns out I have a formula for each of those. If you will go to your homework set, the very first problem there, it says risk and rates of return problem. If you look down at the bottom out in here, and I'm sorry, I use K instead of R here. I forgot to change my notation here. K sub P instead of R. That was the older edition of your textbook. Instead of calling it R, they called it K. I forgot to change my notation on that, so I messed up on it. In any case, we see down here at the bottom of the page a couple of formulas. Yeah, that's great. This gives me the return and this gives me the risk of my portfolio. Now, the return isn't very hard. This is what we would call a weighted average, and this would not be hard for you to learn this one. This second formula is really kind of messy. And I'm not really big on students memorizing formulas that the moment they walk out of the exam, if they remember it that long, they'll forget it. So what I will do is I will take these two formulas, I will cut them out of this problem, and when I make up a problem on your exam, I'll paste it on your problem. So you don't have to memorize that. There's no sense having you try to memorize those kinds of things. So that's what we're going to do. So here's some stuff, and I'm going to go back over this formula, the risk formula here just a little bit, but we'll keep in mind it gets a little bit complicated. Now, in this formula for risk, it says x squared times the standard deviation of a squared plus 1 minus x squared times the standard deviation of b times 2 times x times 1 minus x times another one of those darn Greek letters. And I'm going to talk about that. So let me talk about that letter for you here a second. And I'll write it down for you. Once again, I don't make them very well, but it's called rho. It's called rho. Greek letter R-H-O, rho. A-B is the way we spell that, or pronounce that. And in statistics, if you can remember back to there, the Greek letter rho had a particular meaning, and it was called the correlation. Coefficient. Correlation coefficient. If you remember, what the heck was a correlation coefficient? Oh, that's a hard one. My right hand is A, my left hand is B. Correlation coefficients go from -1 to +1. What does it mean when the correlation coefficient is +1? A's having a good year. Correlation of 1, B's having a good year. A's having a bad year. B is also having a bad year. So as we go through time, if we have a correlation coefficient of 1, they are going up and down like this. Correlation coefficient going up and down like this over time. Correlation coefficient. Okay, up and down together. Now, you name me 2 companies that have correlation coefficients of 1. There aren't any. But that's the upper limit. You can't go like 2 or 3. The most you can be is have a correlation of 1. Most companies have something less than 1. Usually, frequently, it's closer to 0, actually. What would a correlation coefficient of -1 be? A's having a good year. B's having a bad year. And A has a bad year. B has a good year. They do just the opposite. When I get exams from students, I don't like correlations of 1. Okay, that doesn't. That always worries me when I get correlation to 1 on the exams. Okay, it's usually something a little bit less than 1, okay? But hopefully not negative 1, where you get one person gets it right, the next person gets it wrong. That's not so great either, type of thing. So it's a good years, bad year, good year type of thing. So they're always doing just the opposite of each other. So that would be negative 1. What would be a correlation of 0? A's having a good year. B could have a bad year, could have a good year, could have any place in between. So as this one goes up and down through time, this one I've never been able to do it. Can you make your right hand go up and down in a cycle like this and have your left hand be totally Somebody once said, pat your head and rub your belly. And I can't do that either. But even there, I think you'd be patting your head in the same spot of rubbing your belly, which would be either positive or negatively correlated also. But it would have to be going up and down, and this one just kind of flopping around. Now, if you watch me dance, I can show you a correlation of 0, because I have no. But I'm short of watching me dance, and you're not going to do that. I'm truly not going to make myself look like a total idiot. Short of that, but me and my ability to dance and correlating with the music. Correlation of 0. Okay, so that's short of that. I don't know have any other example that might work type of thing. Okay, so we can have positive 1, we can have negative 1, or flopping around 0 type, and any place in between. But those are kind of some extreme points out there. Okay, what I want to do is I want to go back to this question right here. You got these constraints, and I want to ask myself, well, should I invest in A or B, or some of A and some in B, and so forth? And the way we do it is I'm going to do it under the 3 constraints of a correlation between A and B of 1. Then I'll do it for a -1, and then I'll do it for 0. So I'll do those 3 kinds of things, okay? And the way I'll do is I'll set it up as a table. If you look at that first problem, it's set up as a table, and we're going to set up a very similar table. So it'll be x, 1 minus x. I got case of P. A case of P. One set of notes is R, and one set of notes is K. I'm going to drive myself crazy here tonight, so going back and forth between. I apologize. I didn't get my handouts or my homework problems matching with my lecture notes. And what I'm going to do is just look at 3 situations. Or x is 1, or it's 0.5, or it's 0. Now, when x is 1, that means it's all A. And you might want to make that little note. When x is 0, it's all B. And I'm not going to write it here, but when x is a half, what is it? Half A and half B. So we got some of each. Now, when it's all A, x is 1, what's 1 minus x? 0, a half, and 1. Is that what that means? So this is all A, this is all B, and this is 50-50. If you take those 2 formulas on the bottom of the page and go through the numbers, so you go x of 1 times case of A, so 1 times 12 plus 0 times 12, it turns out to be 12%. And the way we can figure this out is this is all A. Listen to what I'm saying here. This will save you a lot of trouble. When it's all A, case of P is going to be the return on A, and this is going to be the risk of A, which is 30%. When it is all B, it's going to be the return and the risk from B. So I just, whatever A is, I write it down. Whatever B is, I just write it down. Now, when it's 50-50, it's going to be half of this and half of this. Well, I'm still going to be at 12%. And if you go into that formula, the one down here at the bottom of the page, and you substitute all of those things in here, I did it for you. I'm not expecting you to do it right. I did it for you. It comes out 30%. If you look at that, how should you invest? All A, all B, half A, or half B? And the answer is they all have the same return and the same risk, and it doesn't matter. But keep in mind, this is when the correlation is 1. And I said there are no two investments that have a correlation of 1. So even though it doesn't matter, you probably can't find a situation like this anyways. Now, let's complicate it ever so slightly. Let's make the correlation between A and B a -1. And let's set up the same table of x, 1 minus x, k sub p, sigma p. And I think it's a good idea, good habit to write down return and risk. Just because later on it'll help when we get to do some other things. If you do that every time, you won't get confused later on. And x takes on values of 1, a half, and 0, and 0, a half, and 1. Remember, this was all A, and this was all B. Does that make it easy to fill in those two rows? So this is what? 12% and 30% and 12% and 30%. Give you a chance to get caught up. Some of you write a little slower than I do. It's one of the things why I like to have people in a live class. I always look around live class and see if people are still writing or not. That means you're kind of like my guinea pigs. I kind of use you to keep me paced right. Now, this still works out to 12%. But when I go for the risk, 0. If you had this situation, which portfolio would you use? The one with this level of risk? No. The one with this level of risk? No. The one that doesn't have any risk. This is investors' utopia, meaning there is no better place in this world to be. Think about it. Year after year after year, you make exactly 12%. Never 15 or 20%, never 5, 10, or a negative 5 or 10. 12%. If Neil could have done that for the last 30 years, I wouldn't have as many gray hairs. I'd be a lot happier. Believe me, I'd also be a lot wealthier because I haven't made 12% year after year after year type of thing. I've had some years I've done much better than 12%, but I've also had some years where I've lost 30%. And the 30% losses, the 50% gains never make up for the 30% losses. That's that risk-return trade-off. It's just terrible on you. And I'd have loved that. Now, the problem with this is there are no two investments that are perfectly negatively correlated. Think about it. You're half A and half B, and you're negatively correlated. What's your return on your portfolio? Right in the middle. Where's the return on the portfolio? Right in the middle. Any point along the line, where's your return? Right in the middle, 12%. Just running right along. Boy, that's a great world to live in. Unfortunately, none of us live in that world. Not honestly. Maybe some of you are doing something dishonestly. Nobody's doing that honestly type of thing. But that'd be ideal. What is realistic? +1 and -1 are not realistic. What is realistic is to have a correlation coefficient either 0, slightly negative, or slightly positive. So close to 0. Now, I picked 0 for a very, very special reason. Bring this in tightly again. As tightly as you can. Whatever will fit on here is get this blown. That's perfect. This term doesn't have a correlation coefficient. This term doesn't have a correlation coefficient. But this big long term here has that correlation coefficient right in the middle. And if you make that number a 0, no matter what all these other numbers are, that big term at the end is 0. That makes the rest of a relatively trivial calculation. Every exam I ever give it on this material, I've made the correlation coefficient 0. And I'm going to continue to do that until I get a class that irritates me so badly that I want to get even. And you're not it. You're not the class that I want to get even on. So yours is going to be 0, okay? Which means even though that's a big, horrendous formula, that whole big thing at the end just disappears for you. And that makes life a lot easier, a whole lot easier. Okay, so let's go back to the overhead here and fill this table in where we have x, 1 minus x, k sub p, sigma p. And this is return. And this is risk. And x takes on value of 1, 1/2, and 0. And this is 0, whoops, 1/2, and 1. Remember, this was all A, and this one was all B. So we can write down 12% and 30%, 12% and 30%. And this is the realistic example. The average of them is still going to be 12%. The key is, what's this number going to be? Is it going to be 30%? No. Is it going to be 0? No. It turns out to be 21%. What does this tell you? The realistic example is the correlation coefficient of 0 or close to 0. Should I put all my money in A like my great-grandfather did or your great-grandfather did if they had money? Should you put it all in B like the other half of our grandparents did? No. What should we do? We put some of it in A and some of it in B. We have what is called a portfolio. And thus, that's the contribution of Markowitz. He says, don't be dumb. Don't invest all in A. Don't invest all in B. Put some of it in A and some of it in B. Now, let's take a look at a slightly more realistic example. In your notes, that very first problem, risk and rates of return, and please, that's good, bring that in. So yeah, right there, that's perfect. Now I've got a little bit different problem here. Before I had A and B with the same return, with the same risk. Let me just put a name on this. This might be what? Bonds? And this could be stock. It could be a new small company and an old mature company. I mean, there's a lot of ways you put it. But they're two different investments. And I just said, let's put some kind of a name on it. Can we fill in this table? And note, true to my word, I kept the correlation coefficient to 0. So when we get down to the bottom of the page, that whole thing just disappears for us. Well, let's fill in that first blank column. What's the 1 minus x column going to be? 0, 0.25, 0.50, 0.75, and 1. If you sum across there, the sum of those two numbers has to be 1. I'm going to make a little note here. This was what? All A. So I'm just going to write the letter A there. And I'm going to write the letter B there to signify that that's all B. This was the return on the portfolio. And this is the risk of the portfolio. Now, two lines on here are pretty easy to fill in. The all A one says, let's see what A has. Here's all A. So this is what? 5% and 4%. And then this is the B1. So this is what, 8 and 10%? So that's why I want you to get used to writing down A's and B's there, because it just leads you to fill in those two lines without any calculating. If anything, it's simple to do it. It's a shortcut, it's better to do it. Now, the return. This we call a linear function. A linear function means it's a straight line. So this is one end of the line. This is the other end of the line. When x is a half, it's halfway in between these two. What's halfway in between 5 and 8? 6.5%. You can go through the formula down here on the bottom of the page if you want. Substitute the values in. But it's a half A plus a half a B, and it turns out to be 6.5%. Now, it's still a straight line. So between 1 and a half, in other words, this 0.75, this 0.75 falls halfway between this number and that number. What's halfway between 5 and 6.5? 5.75, if my math is holding up here today. And similarly, halfway between a half and 0, 7.25, isn't it? 7.25%. So that's pretty easy. This column's pretty easy. Now, where a lot of students make mistakes on the exam, they assume that the risk is a linear function. But this formula down here at the bottom is anything but linear. It's got a square root and squares and sums. We're doing all kinds of funny things. And you need to, some people solve this in Excel. They write themselves a little program and they solve it. Some people bring in a calculator, and you can do that and do it. What you cannot do is you cannot write the program in Excel or in your calculator, store it in your calculator, and then use it on the exam. If you're going to write a program in Excel or in a calculator or any other whatever, you got to do it during the exam. That's that being on an honor system kind of thing. Now, I'm old-fashioned, and I was taught to do these things mostly in my head rather than calculators. I was educated before. I was educated using a slide ruler. So most of you don't even know what a slide ruler looks like. But that's a little bit different than an abacus, but not that much. And so I kind of learn how to do a lot of these things. I'll work it out for you. I'll just give you the answers. You make sure that you can duplicate my numbers. 3.9%, 5.4%, and 7.6%. I would like you to give me one decimal point. So make yourself a little note here, 1 decimal. Because otherwise 4 and 3.9 would be 4, and I want to show that there is a difference there. Okay? Now, there's a B question here. And it says, if you were a really smart investor, out of these 5 portfolios, are there any of them that you probably should not even consider? And there is an answer to that. And the answer is eliminate the first one. Why would you want to eliminate the first portfolio? Let's sit here and think a little bit. If I put all my money in A, I get a 5% return and 4% risk. If I were to go 75% of it in A and 25% in B, what happens? I get a higher return and less risk. Anybody willing to invest in a situation where you get a higher return and less risk? I am. So I don't like all this one. I don't like this one. The rest of these, note, as my return goes up, my risk also goes up. So I can't eliminate. I eliminate this one, and the other 4 I would have to choose among. I can't automatically say one is better than the other. There is a risk-return trade-off taking place. Now, there's a better way of seeing this, and I think I've got time to do this before we go to break here. And another thing that I frequently ask you to do is to do this. I ask you to graph. So let's see if we can make a graph. I remember to bring my straight edge tonight. And I draw much straighter lines, although not necessarily always perfectly straight lines, but they are closer. Now, in mathematics, you were taught that this was the independent variable, and this is the dependent variable. Now, economists, they're crazy people. Now, I also have a PhD, so I can say that. My PhD is in economics, so I can say economists are crazy people. But they call this their independent variable, and this their dependent variable. I don't know why, but if you try and read Markowitz's work, and then you translate it into the way you think mathematically, you always got to rotate things, because they're crazy things. But in here, I want this to be my independent variable. Which is my independent variable, my risk or my return? As an investor, do I choose the level of risk, and that determines my level of return, or do I determine my level of return, and that determines my risk? Well, not everybody is the same on this, but the majority of investors pick their risk. And based upon their risk, they get their return. Now, not everybody agrees with me on that, but that's pretty much the consensus within econ. Now, if you look at Markowitz, he's got risk up here and he's got return over here. And it drives me crazy trying to read that. I can't read things that are backwards. Now, risk, if we look at our data, went from 4 to 10%. So 2, 4, 6, 8, 10. This is very rough. It doesn't have to be to scale. 2, 4, 6, 8, and 10. And my return went from 5 to 8. So 2, 4, 6, 8. And there's 5 data points. All right, let me plot them, and then when we're on break, you take some time and plot these out. In fact, why don't we just go to break now, and when we're on break, take 30 seconds or so and plot out those 5 points. And then I'll do the same thing when we come back on. We'll see if your graph matches mine. So let's take a break here right now.